Nature can be full of grace, gentle, loving, harmonious. Or it can be a cruel jungle out there. For zoos, the basic laws of nature can create problems. But for mathematicians, conflicts can create an opportunity to put geometry to work. And it's as simple as connecting the dots. When you were a kid, you connected the dots. And if you could count, you got a visual representation of a picture.
I did it!
Or you played a game called Dots and Boxes. Both games are early exercises in geometry. Mathematicians play these games too, only these dots connected by lines are called graphs, and graphs are sometimes used to visually display conflict situations. One mathematician interested in conflict resolution is Alan Tucker, Assistant Chair and Distinguished Teaching Professor of Applied Mathematics at the State University of New York at Stony Brook, and an expert in the field of graph coloring.
Graph coloring began with a problem about maps. For centuries, it has been common practice to color maps, with individual countries getting different colors. To make the borders stand out, countries with a common border should get different colors.
For example, let's look at this map of New England. If two adjoining states are forced to share the same color, it's difficult to tell them apart. In order to eliminate this conflict using a minimum number of colors, mathematicians create a graph and use a procedure called vertex coloring. Alan Tucker explains.
Let's set a dot in each state to represent that state. This dot is called a vertex. Now draw a line between the vertices, or the states, that share a common border. This line is called an edge. If we remove the geographic map, we have a graph. A map coloring problem now becomes a graph coloring problem. We want to color the vertices of the graph so that any two vertices joined by an edge have different colors.
Building up the coloring of the graph is done step by step until all the vertices are colored. The graph now contains all the information we need to color the map.
About a century ago, mathematicians became interested in the problem of determining how many colors were going to be needed to color different sets of maps. For many years, this was one of the most famous unsolved problems in all of mathematics. In 1976, two mathematicians at the University of Illinois, Kenneth Appel and Wolfgang Haken, came up with a proof that showed that four colors always work.
Seeing how useful vertex coloring graphs were in solving map coloring problems, mathematicians soon began to utilize this technique to address other conflicts. Zoos want to design habitats that simulate a more natural environment. But if there's conflict between different species of animals, they can't share the same habitat. For purposes of example, here are the animals in our zoo. I'd like you to meet them.
Amanda the tiger. Candy the oryx.
Debbie the zebra with Junior.
George the giraffe. Kanga the elephant. Maribel the panda. Stefan the rhinoceros. Winifred the American bald eagle.
One of the zoo planners thinks that he has found a way to place these 8 animals into 4 new habitats with no conflicts. But with each new multi-species habitat costing as much as $2 million, can the number of habitats be reduced? Let's use vertex coloring to find out. To start, our resident zoologist provided a list of the 8 animals and their conflicts.
First, we need to build a graph to represent the conflicts among animals. Let's create a vertex for each animal. If two animals are in conflict so that they cannot be in the same habitat, then draw an edge between them. For these animals, we construct this graph.
In the map coloring graph, we assign different colors to vertices so that states in conflict, those with a common border, would not share the same color. Now we assign different colors to vertices so that animals in conflict will not share the same habitat.
Say we color Amanda red. That is, Amanda goes into the red habitat. Then suppose next we color Candy blue. Candy must be a different color from Amanda since there is an edge, that is a conflict, between Amanda and Candy. If two vertices are not joined by an edge, they can have the same color. That is, animals not in conflict can be in the same habitat. Let's also color Debbie blue, since Debbie's also joined to Amanda but not joined to Candy. Then say we color George gold. Then Kanga must be red, since Kanga has conflicts with Candy, who is blue, and with George, who is gold. Mirabelle must be gold because of conflicts with Amanda and Candy. Next, Stefan must be red because of conflicts with Debbie and George. But now Winifred has conflicts with Debbie, who is blue, George, who is gold, and Stefan, who is red. Winifred needs a fourth color. That is, Winifred must be in a fourth habitat. So we still need 4 habitats.
Wait a minute. Is this the best we can do? Isn't there some guideline in geometry to help?
The answer is a partial yes. Fortunately, mathematicians like to develop theories that give general rules for solving a problem. There are a number of theorems that specify how many colors might be needed to color different sorts of graphs. One of the theorems is called Brooks' theorem. Brooks showed that, with one exception, if a graph has at most 3 edges at a vertex, then the graph can always be colored with 3 or fewer colors. With 8 edges at a vertex, 8 colors. With 15 edges at most at a vertex, 15 colors.
Well, this graph has 3 edges at most at a vertex. According to Brooks, we should need no more than 3 habitats. Where we went wrong was in how we assigned colors. So let's recolor some of the vertices. Okay, let's make George blue since he's not in conflict with Candy and Debbie. Since Winifred is in conflict with George, move her into the gold habitat.
Now it's only 3 colors, or 3 habitats.
We now seem to have saved the zoo $2 million, and the animals obviously approve. But will Brooks' theorem always work?
No current theorem or coloring scheme works all the time. Every method invented to date works well some of the time, and then has unexpected problems other times.
One thing, however, you can depend on. There will always be a need to resolve conflict situations. Whether it is a conflict in transportation scheduling, broadcast or cellular phone frequencies, staff meetings, or even school exams, young mathematicians interested in vertex coloring will find new and fascinating challenges as they head into the 21st century.